Awesome. Let's go ahead and get started. This is where we left off on Wednesday. We were talking about the basic mechanics of the function prototype and how that really has a part to play with regards to really what I call the three parts of a function. The prototype can be thought of as almost like a contract. I'm saying when I have this declarative piece of code, somewhere at some point in this program, when you compile it all together, there will be a function called myMac. It'll have these inputs and that output. That's all that the prototype is doing. We saw that we technically can get away without having a prototype by making sure the actual function definition happens before the caller function, but that's kind of a hack and a little wonky. So we generally want to have these prototypes. We then have the actual implementation of the function, which, as we have started to see, and we'll see quite a bit in Lab 6, can be in all sorts of different places. It can be in the same .c file that your caller function is in. It can be in a totally different C file that you compile in at the same time. Or, as part of that Lab 6 experience you're going to do, it can be part of a library. When we call those libgd functions, like when we're doing our image processing, and we call gd image create or one of the many functions we are using, the C source code for that function is very likely not even on our computer. When we installed the package to be able to do development for that particular library, what we're actually installing are pre-compiled versions of all the code that's part of that library. That's just referred to as a dynamically linked library. The other term you'll hear used is a shared object file. It's kind of like a program, except it's not an executable. It doesn't have a main function. It's just the binary blobs corresponding to all the functions that are part of that library. So in Lab 6, you may get the impression that I'm making you go through some unnecessary steps. Unnecessary is in the eye of the beholder, but I am having you go through those steps of, I'm going to write this function in part 4 of the lab, and I'm not going to copy that code over to part 5. I'm just going to copy over the shared object, the binary blob. And I'm going to show that, in fact, I can still run that code from part 4 in part 5 without having access to the source at all. What you still, though, need in that case, not the source code for the function's implementation, not this box here, but you still need these things. You need that contract. Again, you're telling your compiler for your code, hey, by the way, there's a function myMac or gd image create or whatever the digital logic simulation function in Lab 6 is called. It exists somewhere on the system. You'll find it eventually by the time you're done compiling. It could be in this other binary blob file that gets linked in after the fact. And then finally, that third part of the implementation is then the actual calling of the function in your code, which I think we inherently kind of understand because we're calling functions from the first day of class when we printf hello world in this class. But I think we have to be just a little bit more aware of what's happening when there are our own functions versus some other predefined functions. What is happening, I'm trying to visualize this here, how well it comes across, it's not that clear, is when we have the calling of the function, we are going to then replace the variables corresponding to the inputs with that function with some local variables defined inside that caller function. And that's all that was happening in that myMac replit code we have here. We could have had them be constants, but intentionally we defined 3 variables. We just called them variable 1, variable 2, variable 3. And as part of that calling convention, and eventually, as you learn more about computer processors and how they're organized and a little bit more about how compilers work, we'll understand the direct mechanisms by which this happens. But as part of that calling procedure, what happens is a copy of these 3 variables are copied to a specific place in memory such that when we actually have the code for the function itself, those 3 values get copied into the 3 variables and the corresponding memory locations so that the code that does m times x plus a takes a copy of those variables. That's kind of how we would want it to work. We have a function that encapsulates functionality, so nothing in this function changes anything that happens in the caller function. It's all very local. All those variables are defined local. Changing temp here doesn't change any temp variable in the caller function. That's correct and that's good, but sometimes that can be very constraining in terms of how we write code, because we have to really think about, okay, I'm tearing off this piece of functionality because I'm going to want to reuse it, and it has to be kind of self-contained. And that's a good thing, and there's other programming languages that force you to have everything be completely self-contained. have no state whatsoever associated with the function call. C isn't quite so limited like that, but it does force us to kind of limit how we're sharing data between caller and callee functions. We'll talk about today next some ways we can kind of work around those limitations, because again, for a toy example, it's not a problem. Take 3 values, generate a value, you're done. Return that value with that return keyword. But when you're doing more complicated things, it can be hard to kind of cleanly split things between caller and callee function. Well, it's that final part of that calling procedure. Not all functions are required to have a return if they don't return a variable of a given type. And so that's a void function, which we've seen. We can have functions that just do something that don't actually return something to the caller function. But it's much more common that, again, if we think of this as our black box for our function prototype here, that a function is something that takes inputs and generates an output. That's the whole point of having that piece of code. It's a machine, takes some inputs that you specify, generates some output. And so when we call the function, we need that return statement to determine what is the actual value that once we've called this function is going to get overwritten or used in some mechanism. So I didn't mention it, but that's what that variable for now is doing here. We take var1, var2, var3, treat it as inputs to this function. We do some math, we do some logic, we do something inside that function, and then the return statement specifies what is the value we actually want to correspond to the output of this function so that we can use that value and do something with that value. The reason this example isn't that great at demonstrating that is we don't actually do anything with the, we don't do anything with it is the only problem here, right? We generate a variable for, but then we don't actually use it. But we could have printed it out or something like that, and that would have been fine as well. That's why we need that return value. It is usually, but not always, a single return value statement per function, but you could have returned within an if statement. If m is greater than 3, return this, or if m is less than 3, return this. It is generally the last kind of control flow in that function. We start at the very top of the function, we work our way sequentially kind of down from line 3 all the way down. When we hit return, we're out of that function, and we return whatever the value is in that variable that we specify. You'll note here for this example, we were kind of playing around with it at the very end on Wednesday as people were walking out of, this ability to kind of define the prototype separate from the implementation, separate from the calling site, does lead to kind of a natural code organization. A lot of this becomes opinion more than just, a necessary way to do things, but it's pretty common to recognize that in your program, you're going to have a lot of functions, and we would want to then have a separate file that defines, amongst other things, all the prototypes that may be relevant for your code. In this case, there's just one function, so we have just one function prototype, and we put that in that main.h file. It doesn't have to be called main.h. Whatever we call it, just like we include standard io.h, we also would want to include main.h so that it's essentially a copy-paste. When I do include, it's saying find this file and find it local to where I'm currently, the directory I'm currently in, and literally copy-paste the contents of that file into my file. So it's a way to just kind of cut down the lines of code to kind of separate out prototypes from implementation. And then once we have that prototype, this code in this file will compile without any problem. It'll say, okay, I'm expecting a function that's myMac that takes 3 floats and generates a float. I'm calling function myMac that takes 3 floats and generates a float. As I compile this file by itself, I'm happy. I don't know where that function is yet. I don't know what it actually does yet, but this file is itself able to be compiled because there's kind of a standard agreement as to how we actually call functions, and we compile in the code to call that function. There's then going to have to be a final step, that's the so-called linker step, that takes all the things you've compiled, including now a separate file that would include the actual implementation for that function, and for want of a better word, smushes it all together. Okay, the correct word is it links it all together. It determines for all the things you've defined in your code, all the symbols in your code, all the names of functions in your code, where are they found? It just does a lookup. At that point it says, you have this main.c, and now it's a binary blob, main.o, and as part of that you are calling a function myMac that takes 3 floats and generates a float. All right, linker, I'm the linker. It's another piece of software like anything else. where is that function? And if it can't find it, it's not going to link, and you're going to get what effectively looks to be a compile error. But if it can find it, and it'll find it in mymac.o, it then determines what address in memory that should correspond to and completes the rest of the compilation process for your program. So this is a pretty natural way of organizing things. You know, whether you have to organize things this way or not really depends on, you know, the scope of the code you're working on, whether there's, you know, multiple developers working on it in parallel and you really kind of want to separate concerns between who is working on what. But at the very least, creating your prototypes as early as possible is a very good way to get started. I can create that prototype and create, let's say, like a stub implementation of it that doesn't do anything, that just returns 0 every time I call it. I can then have a program that at least does something that compiles all together, and then I can worry about the implementation of this at some later point. Also, working on your prototypes first forces you to kind of break down the problem, which is what we want to do, right? We don't want to just be sitting down and typing. We want to have a thought about, okay, what is the actual structure of what I'm trying to do? What problem am I trying to solve? What are my inputs? What are my outputs? That same kind of problem-solving process on a micro scale is what goes into this task of creating a function prototype. Okay, I have something I want to do. It's not the whole thing, but it's some part of the thing that I'm trying to implement here. What inputs should that subcomponent have? What output does it need to generate? What's a reasonable name to call it? All of those questions have to be answered by the time you've designed your prototype. The actual implementation of how you go about and do it, you can put that off till some later point. Or that's your lab partner's task to take care of that challenge. I mentioned this in Discord, but that's also unique to Lab 6. You cannot just go your own way on Lab 6. Have people discovered that already? You cannot do part 2 without having done part 1. And likewise, I guess, for all the parts. Not to be, you know, overly negative here, you also can kind of get quote-unquote correct results in Lab 6 without following the instructions as written. But the TA is at least supposed to take off points if you don't do that. So do try to follow the instruction, which is building functions to simulate individual gates, using those functions to build up more complex functionality, and then ultimately kind of gluing it all together for part 5 of that. You can get something that kind of generates a reasonable output without actually doing that. But that also defeats the purpose. So you're going to lose at least a few points if you wind up doing that. Otherwise, you know, when do you choose to make a function in your code? When I tell you is correct. But otherwise, there isn't like a hard and fast rule. I would say reuse is a good thing to look for. XOR2 as a function that is part of Lab 6. It's a logic gate. It's a universal logic gate. If I'm going to be working on logic simulation as part of a bigger project, might be good to have that as a function. I know that's a bit of a squishy, you know, definition for whether or not you want to have a function. That's kind of the best we have to go with, which is here's some functionality that seems pretty important. I may see myself using this again in the future. In this current project or in future projects, make a function for it. Another very hand-wavy kind of rule of thumb is the current function you're writing on is just fitting past the single page. You can't see the entire code base you're working on at any one given time. That's a function of what your font size is and what your screen resolution is. So it's not the same, or whether you're using multi-monitor setup. So that's not the same for everybody. So obviously that can't be a hard rule either. But once you start to see the complexity of what you're working on within a single function, whether it be main or some other function you're working on, once you're starting to see that spiral out of control a bit, whether that means you need to refactor it into separate subfunctions or not, it's at least a time to step back and say, okay, this code is now 700 lines long. Am I doing something wrong? Could I have actually saved a lot of lines of code by kind of taking this thing I'm copying and pasting and doing over and over and over again and putting it in a function instead and making it a lot easier to kind of break it down? And as always, as part of our problem-solving process, you should always be asking, especially if it's not a homework assignment and if it's something you're building for its own purpose, am I reinventing the wheel, right? If the code I'm writing is something that already kind of exists in reasonable shape elsewhere, certainly in a officially supported library or at least a well-known, preferably probably open source library that I can inspect the code myself, maybe you just use that instead, right? Use somebody else's code is always better than writing your own code if it does what you need it to do. Briefly, although I don't know how much we need to grok this long term, but the implications of it we do need to appreciate, is that what happens in memory when a function is called. This is more of an assembly kind of type of topic than it is C programming, but it does relate to implications from the programmer's perspective. When a function is called, there's going to be a separate region of memory that's going to get allocated specifically for that function. That's referred to as a stack frame. And you may have heard the term, before, we're going to place this on a stack. You may have heard me say that or not, but that's what it's referring to. When I call a function, all the variables being used for that function, all the input parameters and return values for that function get placed in a separate region of memory. What that region of memory looks like is very system dependent. So there isn't one answer, but almost all processors, binary interfaces, operating systems use a stack frame. So that's pretty universal. What the stack frame looks like depends greatly on what particular system you have here. So when I have a function that calls my func, it's going to have a region of memory dedicated to it that's going to have, in addition to other things, copies of the input variables, as well as information necessary to get back to the caller function, the actual address in memory that gets us back to the caller function. That is part of effectively a quasi-standard referred to as the application binary interface. It's a standard for interoperability that allows me to write a function and compile it with one compiler, and by and large, it'll work when I link it together or when somebody else links it together at some future point in time. It tends to be very architecture specific though, which is why if you download the binary you created in Replit and your laptop is an ARM-based M2 MacBook, not too many MacBooks in class, things have kind of shifted. Double E's are more Windows people. That's interesting. Software E's are all about Macs. But it would likely, and I think, essentially be guaranteed to not work if you did that. Not just that the binary ones and zeros for the instruction opcodes would be different, but this mechanism by which we kind of agree that, hey, here's how you're going to allocate and reserve memory for function calls is going to be different on a system-by-system basis. It's not so dire of a situation because certainly within the Linux world in which Replit is based, there's been a well-established standard over a period of decades now, and code generally is going to work, and if not, it shouldn't be that hard to recompile to get to work on a given system. But the implication for us as, go ahead, yeah, sure.
How do variables declared outside of the main function work within the function stack?
They don't. So we'll talk about that. So what I kind of am hiding here, but it's correct to say, every function has a stack frame, including main. So main itself and the variables you declare inside main have their own location in the stack is where they're put. So by default, and I'm getting to that, so this is directly relevant here. By default, as we are calling these functions, and this is my Mac or printf or scanf, the program is copying its assigned variables, transfers controls to that function until it finally gets a return statement. Each variable inside your function is going to have its own scope. We already talked about scope for like for loops and if statements. You can define variables inside those curly braces. The same is 100% the case for function calls as well, except that the variables that are defined here as our inputs and potentially our output are also within the scope of that function. Consequently, by default, modifying any input variables has no effect on the variable that's passed as an argument.
The variable is declared outside of the main function. So like if your include is defined, so is it global?
Yes. That we'll talk about that as one of the potential workarounds. Yeah, absolutely. So that's another region of memory that gets dedicated for things that are not part of a local function call, and they are global. We generally don't want to put data in our header files, but we can define references to external data in our header files as a more common approach we want to take here. But this statement, it's even bolded here, is pretty important. And maybe it's obvious because we already have the curly braces rules for our scope of variables. Maybe it's obvious when you're calling other people's functions that calling that function doesn't change anything in my main code. But when you are now responsible for writing your own functions, you have to think about that kind of separation of concerns. I've called my Mac, and it's going to return one value. And it's not going to change, by default at least, it's not going to change anything else in my caller function. That's considered a good thing in the sense that's why we have a function. We've encapsulated this one-off piece of functionality, and it's only changing one value as we get a return result back. That's also limiting, and also we have to really think about, okay, as I have my function, what if I want to change more than one thing? What if I want to have some separate side effect of the calling of that function? And C does provide us several workarounds, going to your question before, to deal with this particular issue. Use all of these workarounds with care. They are all what's referred to as kind of code smells, which is a way to refer to something that it's not wrong. It's just a sign that there's likely other problems with your program if you're using it heavily. But that, again, so it's not a bug. It's not wrong to do this. One of these workarounds is using so-called global variables. There's no global keyword in C, unlike there are in certain other functions. But if we do sometimes need to have variables that have some state, that keep track of some information about the entire execution of the program, and we want to have all or multiple functions to be able to read and write and update that variable, we can in fact define variables. We haven't done that too much this semester, outside of all of our functions, and they would have both global scope, meaning every function would be able to access that variable, and they can then be not just read, they can also be written to from all of the functions we have in our program. Side effects in our functions is generally bad. It's a code smell. It's bad programming practice. We sometimes have to do it. General code guidelines that I have read and my own just current practice are that if you truly have some global program state and the whole program is in service of updating that state, having a single and maybe a single structured variable that keeps track of that state is okay because it's kind of an understood part of your program. But in general, you never need to use a global variable. It's a workaround. It maybe simplifies the design of other functions here. Let's take a look at the example of global data in practice. The fact that it's called myGlobal is just our name for it. Again, there's no global keyword. It's defined like any other variable, but it's where it's defined that is a little different here, right? It's outside of function main. It's outside of any other function. It's just kind of sitting there in the ether. Could be in this file. Could be in another .c file. Doesn't have to be before your other code. It could be at the very bottom. Probably should have it up front and early. And then we have a function called update that takes an integer as input and just kind of multiplies it by the value of my global here. So it just does a multiply and then returns that temporary value it created like a regular function like we were previously doing. But then it also does my global plus plus. So when we now call that function update 3 different times, update A, which has a value of 1, update B, a value of 2, update C, a value of 3, my global starts at 3, but after the first time it executes, the value of it will be 4, and then after the second time it executes, the value of it will be 5. So it'll be 3 times 1, 4 times 2, and 5 times 3 is what will get calculated here via this function. I might have said that wrong, but that's what I meant. 3 times 1, 4 times 2, and 5 times 3 is what gets calculated here. That can be a very useful thing. It can also be tricky, right? I'm trying to debug why the value isn't what I'm expecting. And a very common thing we want to do, right, is, okay, I'm going to call update of A, and I'm going to call update of A later, right? That's a pretty common thing. Maybe not on consecutive lines of code, but in a for loop or at different points in your program. And because of this so-called side effect, because of this global variable that gets updated in this function, it's a side effect because I'm doing the same thing twice and I'm getting different results. I called update of A twice and I got 3 and then 4. Which, if that was our goal, that's perfectly fine. But in terms of tracking down bugs, in terms of understandability of your programs, readability of your programs, that's harder than a program that maybe takes a second input for the value to be multiplied against and that you update it in the caller function. What's a function we've used quite a bit this semester that clearly has some side effect and or global state associated with it? That I call it twice and I get different results. So it's not always a bad thing. Random, absolutely, right? And it has to be. If it returned the same value each time, it wouldn't be a very good random function. My My best guess for the mechanism in use, we could look up the source code for it, but I haven't, is using this third mechanism here. I'll get to the second one in a second, in which, in terms of how this gets implemented, it is essentially the same as using a global variable. So the difference is really the programmer's view of what's happening here. Conceptually, what we're doing with this keyword, and the keyword is static, is we are telling the function that we actually want to remember the value of that variable between calls to that function. So unlike there being no global keyword, there is something that gives us a kind of similar sort of view. It's still local in scope, so other functions could not use this value of the variable x. So it's still local to x, so that's still a nice encapsulation of our variables. But that static keyword, static in contrast to dynamic, I guess, or permanent versus temporary, there's other keywords that could have been used there. Static keyword then says for the variable that we define, and we would have to potentially initialize it, at least for the first time we execute it, that value of x is going to keep its changed value between calls to that same function. This is kind of a toy random number generator. It's kind of intentionally hard to read. So the example I have here is just a more simple use of functions, of variables that are static here. Similar to what happened with our global variable, we have a function. In this case, to show this off, we don't really need any inputs or outputs to it. We call the same function a bunch of times, and we're going to get different results because of part of it, the first time we call it, x is going to be 0, and it's going to increment it. Then the next time, even though we look at the first line of code and it says x equals 0, the value of x will be 1 the next time we call that same function. Kind of similar to global variables. Equal challenges with debugging, right? I'm really expecting x to print out 0, but all of a sudden it's printing out 1. Why is that the case? Well, you then have to kind of dynamically trace your program. You can't just statically analyze your program because you have to know, well, how many times did this function get called and by whom? Anyone who's calling that function in your program is going to update that value of x. That can be what you want. For random number generators, that is exactly what you want, but it can be very hard to track down when things don't work the way you would expect them to. So we call the same function. If we removed that static keyword, what would it print out instead? Just the same function gets called, the variable gets initialized local, it's not a global variable, local to that function, it's initialized to 0 each time, we print out 0. We're allowed to increment that variable, do whatever we want with that variable, but it's not going to keep that result after we've called that function, because it's local to that function, both in scope and literally in terms of where in memory that variable is going to be located when it's executing. So that static keyword, arguably I think it's still better than global, because global, there is no keyword. You have to know what to look for in your code to know that something's global. And then in terms of scope, in terms of analyzing it, you are still kind of just looking at one function in isolation. When I have a global variable, again, it's not a bug, it's a code smell. Here I only have one function that updates it, so no harm. It's pretty easy to track down. The distinction is pretty subtle between static and global in this use case. But there's nothing preventing a poor programmer from having 70 functions that update that same global variable. If it works, it works. But if it doesn't, how do you then track down exactly what function is causing the value of my global to be not what I'm expecting? You also have issues if you have programs that involve some sort of parallelism or concurrency. I have two functions that are potentially updating that global variable. Which one got there first? And what should the value be afterwards? That is a whole separate kind of branch of software development, software engineering in understanding, tracking down, fixing concurrency bugs. I think for better or for worse, fortunately, we don't have to deal with that this semester. That's static versus global. Another approach where if we potentially want to modify an input variable, or is kind of a hacky sort of workaround to return more than one variable at a time. We've talked a little bit about in practice the syntax with our scanf, but we do so by having our functions take not the value of a variable as their inputs, but instead we're going to be effectively sending the memory address of that variable as the inputs to a function. When we refer to this term of a pointer in C, That's all it's meant to allow for us to do. We're declaring something as being a pointer to a variable. We'll talk more about this in a couple of weeks. But in terms of this workaround for functions, instead of saying I want int as my inputs, I'm saying I want an int pointer, an int pointer, an int pointer. Instead of passing A, B, and C to a function, I'm going to pass the address of A, the address of B, and the address of C. And there's a little bit of a trick that winds up happening here. All the stuff I said about stack frames and where things are located and how functions have their own local scope, that's still true. That doesn't actually break that assumption, that kind of contract with our functions. What has changed is what I'm explicitly passing into these functions as these variables are just addresses in memory. Address 1000, address 2000, address 3000. And then syntactically, this looks really bad, and we don't have to become experts in this syntax quite yet. I'm not actually changing the addresses, I'm following the address. Change or read what's at that location 1000 in memory, or at that location 2000 in memory, or at that location 3000 in memory. So my scope is still local, but I'm updating memory, and I'm updating kind of arbitrary locations in memory, and that allows me to effectively then update my variables in my caller function, and as many of them as I'd like to, without even having a return, by updating them by just changing what happens to be in memory at that particular location. That is the whole point of using pointers. For now, just be aware that we did do that with our use of scanf. Scanf could update as many variables as you wanted when you called it, because it was doing effectively that. And the way it works is by passing addresses and not by passing the values themselves. A little bit of circular definition there, because the address itself is a type of variable. It is a type of variable, a pointer variable, that stores an address. I cannot change the actual address because the same local scoping rules apply. I can't change where A is located. I can't change the value of that address and have that be reflected. But I can change what's in memory at that address, because C allows you raw access to memory to directly change the value of things in memory by providing an address. This one is unfortunately called function pointers versus functions with pointers, but we'll take a look at it. We have A, B, and C. I am passing to this function not the values of 1, 2, and 3, but whatever those addresses correspond to. We've played around with printing the addresses. It's not very helpful. It's just, yes, they're at some location in memory. I'm passing in location of A, location of B, location of C. And then for now, we kind of just take it as an article of faith that when we want to work with pointers in our code, we use this, it kind of looks like multiplication syntax. It is the pointer syntax in C. I'm declaring my inputs to be actual pointers and not actual integers. And when I want to actually update what's at that location in memory, I follow that pointer. That syntax intentionally looks bad. We will spend a full week just focusing on that syntax. But the result is, what winds up happening here, it's called doubler. Take the value at that location, add it to itself, and store the result at that location in memory. So double the value of in1, because double the value of at that memory location pointed to by in1. Same for in2, and same for in3. So when I have A equals 1, B equals 2, C equals 3, we don't touch A, B, and C. We're messing with just local variables here, but we're messing with the locations in memory of A, B, and C. So it should print out not 1, 2, and 3, but should print out 2, 4, and 6, because we've doubled those values. This is not considered a code smell. This is a very common approach to change more than one thing when we're calling a function, because otherwise we're pretty limited. If I go back to our original myMac example, unless we use those pointers, I can only return one value from my function. That can be useful, and it may force you to kind of think, okay, how do I write a function that there's only one value of interest? And there's even more workarounds we'll learn over time here. But it can also be very limiting. Syntax is a little bit cleaner, whereas now with this syntax, we don't have to change those values pointed to in memory. I could choose not to do that third line here. I don't have to change it. So now it'll be 2, 4, and 3. But I now have both the opportunity and or the risk associated with being able to change those values in memory. If this is what you wanted the code to do, it's perfectly appropriate. But now you do have effectively that kind of hidden side effect. it's not as hidden in my opinion because I'm being very explicit that I'm passing pointers. And you generally don't want to do that unless you're wanting to change the value of those variables pointed to by those names. Yeah, sure.
Adding where those values are definitely replacing, right?
Yes.
So what would be the difference if we didn't have the pointers?
Like if it was just in1, in2, in3 as ints. Yeah, let's and let me do that as a separate function because I feel like I'm going to break it pretty badly if I try to refactor that function. If it, I hear what you're saying, and give me a second to just do it, which would be in1 equals in1 plus in1. I hear what you're saying, and then yeah, 2 and 3. Well, and let's call it. Let's call it before we call our other one. We'll call doubler 2, and now it needs just 3 integers, so it doesn't need any pointers, it just needs the integers. It's a good question, so I like that we have this here. Based on our admittedly fairly fresh understanding of kind of the default contract of our functions and what should be happening, I call function doubler 2. What happens to A, B, and C? Well, not exactly. What happens to A, B, and C before anything happens inside that code? Let's make sure I have the appropriate, I guess this diagram's the best I got for now. What happens to A, B, and C, or just A and B in this example, is a copy of those values of those variables gets put in this separate region of memory, gets pushed on the stack, gets put in memory that is local just to that function, which you are allowed. This syntax is perfectly valid to do whatever you want with those variables once you have them in there. Set them to 0, double them, do whatever you want. But that is a copy of the original variables. Changing in1 has 0 effect on A and B and C, kind of by design. Likewise, in1 does not change, star in1 does not change the address of A, the address of B, and the address of C. But because I'm directly updating memory, it's a side effect. I'm changing what happened to be in that original location in memory. So this should print out 1, 2, 3, and then 2, 4, 6. So doubler 2, the one that is just locally changing values. I could print out those values inside the function, it would be 2, 4, 6, but the value of A, B, and C won't have changed. That may make perfect sense to a lot of you right now, but when you're working on your own functions, don't be like unhappy, upset, intimidated if like you're struggling with that concept. This understanding of side effects of functions, the fact that in1, in2, and in3 are changing, but A, B, and C are not, is what makes this a non-trivial, why it's its own sort of standalone topic. So you have to really ultimately think about the problem. Thinking about the function prototype can help with that. Hey, do I need to have global variables or static variables or pointers in my functions? But that's not trivial, so you'll want to take your time with it. The more you think about it up front, the less headaches and refactoring you'll have to do later here. There are other examples. Another one that we will start to use quite a bit here. Again, part of the challenge with this topic is just like with the pointer topic, we're going to get into this in a little bit more detail later on, but in terms of writing your own functions, it's important to be aware of that now, is you can also have array variables as inputs to your function. But in C, for better or worse, you cannot have array variables as an output of your function. That is a design decision that likely made sense very early on and still makes some sort of technical sense, but is also just a restriction you face as a programmer. So just remember that. Hey, I really want this function to return an array. You can't do it, at least not using that return keyword. But what winds up happening in C, and the technical term for this definition and this reasoning is that arrays and pointers are effectively equivalent in C. They both are corresponding to an address in memory, is that when we pass an array variable as an input to a function, and we then update that array variable, this example doesn't actually show it, and we update an array variable inside that function, that array variable in the caller function also gets updated. So, I don't know, this isn't easy, this isn't necessarily fun. I just showed you in1, in2, and 3 can change, but it doesn't change A, B, and C. When they're just individual scalar variables and not arrays, that is a correct statement, and that should still be your default assumption. However, we already did the static one. When we have, I got a lot going on here, we don't need to go through all of this. When we have a function input that is an array, because ultimately what the compiler does when it sees this, and this is what is meant by array and pointer equivalence in C, is in order to compile the code for that, it takes that array syntax that is very nice and clean and it turns it into pointer syntax ultimately. An array is a programming language construct. From the implementation, it's just addresses in memory and calculating what address in memory I should be updating things. So ultimately, this is defined as float array with the brackets indicating an array of undetermined length. It is ultimately essentially equivalent to doing that, which is declare a pointer called array. And in fact, unless I'm terribly wrong, this code should still compile and should still work when I do that, and it does. But let's go back to the original version of the code. So when defining our arrays, we've talked about how sometimes it makes sense to be very explicit defining the length of our array. Other times, and certainly if we're initializing the array, it sometimes makes sense to not actually, and let the compiler infer what the length of that array is. When we have our arrays as inputs to a function, the most common practice is not to define a length there. But with the trade-off and or the extra thing you have to be aware of, it's very common practice then and recommended practice to explicitly have a separate input that is referring to the length of that array. Somewhere, somebody has to know how big my loop needs to be. How many valid things are there inside my array for this function to process it. This is a nice function though, in that unlike if I'm doing this within main, here I could call this function on all sorts of different arrays of different lengths and it should still work. It just needs to know the start location of that array, it needs to know the length of the array, and can add up all the values of that array. The only time we tend to not have to send the length information as a separate input are if for whatever reason there's kind of some sort of standard or specification we're following that it's kind of assumed or defined elsewhere what the length of our arrays are. Pound defined n is fine, but still it may be useful to have a length variable. Or if we have our C strings, right? If we have our null terminated strings, we can still pass the length information, but we usually don't need to. They're null terminated. We can figure out the length of our string. We can call string length. We don't need to explicitly pass in the length information. We can, but we usually don't need to. Arrays are effectively pointers to that region of memory, so those pointer rules are still going to apply. So that when I call, I have two different functions here, where I'm first going to call function sum, and here I just use the syntax I use, still just the name of the array as the input to that function. So you don't use the bracket syntax here. I just pass the name of the array as an input to the function, and then it works as if I've copied that whole array into that function. But the way it works in practice is that effectively what we're copying is the address of array. The address of that first element in an array, a pointer to array. So consequently, this other function, which is called increment, that does for I equals 0, I less than length, I plus plus, add 1.0 to each element in my array, that does give me that effect of changing the initial values that were passed into that function. Again, going back to this example where the doubler, we lost it, where this one did not change A, B, and C, because it is an array, when I call increment on my array, which should be right here, it will in fact change those values. And that's what's actually showing being executed here. Sum function, we print out 1, 2, and 3.4. We add them up to get 6.4. After calling function increment, the values are 2, 3.0, and 4.4. They actually did get incremented via that function call. That's a lot. So, I don't like you using slides as a textbook for any topics in this course. But when working on Lab 6 and then especially Lab 7, which is going to be another one of those fun 2-week labs, and it's probably the hardest one this semester will be Lab 7, you may want to have a couple of these slides open to remember, okay, I'm defining my own functions. What are the rules? what are the workarounds for those rules. But it's your first time doing it, so it's very natural to have just challenges along the way. There's a design exercise I wanted to get through, but I think that'll be a good use of our Monday time together. Otherwise, let's leave things here for today and enjoy your weekend. Come see me in office hours if you have any other questions at 1 o'clock here.